Thank you, Julio, and thank you to the organizers for organizing such a great workshop and for inviting me to give a talk here. So this is a real change of pace compared to the last talk. So rather than trying to define quantum field theory and all of its generality and all of its mathematical rigor, I'm really just going to be focusing on how do you compute an expectation value in a particular class of spacetimes, namely black hole spacetimes. So my apologies if I offend the mathematical sensitivities of the more mathematical community among us, but this is not going to be particularly rigorous. So this talk is based on work that I'm currently doing with Adrian Otterwill at UCD and Cormac Breen at Technological University of Dublin. So the references are here if you're interested in the finer details. So let me just zoom out momentarily and just I guess define what I mean by semi-classical physics, which is the context in which I'm interested in. So we can consider some physical process characterized by three scales: a mass scale, a length scale, and a time scale. And we can construct three-dimensional numbers from these three scales, which will tell us how important special relativity, gravity, and quantum effects are, respectively. So assuming for now that that the first quantity here is of order one, that the kind of physical process that we're interested in is always relativistic. We can plot on a log scale these two dimensionless quantities here, epsilon g and epsilon q, just to kind of examine the parameter space and the regimes of validity for the physical processes we're interested in. So that's what this plot here is showing. So any constant script L here, which is the length scale of the physical process I'm interested in, will just be a straight line in this log plot with a slope of -1. So this is the Planck length, for example, here. And so this is some other length scale that's much larger than the Planck length running along this line here. Okay, so moving in this direction here is moving towards the weak gravitational field, and moving in this direction is the strong gravitational field, and moving upwards is moving in a more quantum direction. So where we're interested in is up in this kind of top left-hand corner, up in this semi-classical regime up here, where we're interested in quantum effects, but we're not considering, say, strong gravitational effects associated with the physical process that we're examining. So that's kind of the regime of validity for the context of this talk. So in the semi-classical gravity, we're going to be treating gravity essentially classically. I mean, we can talk about perturbations, but we're going to be treating gravity essentially classically in other fields, quantum mechanically. And oftentimes the starting point for this theory is to assume the so-called semi-classical equations, where you basically replace the classical stress energy tensor for some fields that you're interested in with the quantum version of this stress energy tensor. At least naively. I mean, this equation turns out to be wrong, but at least, and there's lots of issues with it, but at least naively, that's your starting point. Okay, well, to see what's wrong with this equation, there'll be a bit of overlap here with the previous talk, but let me, for simplicity, just assume that we have a scalar field. Then we can write down an action for that scalar field in the usual way, and varying with respect to the field gives us the Klein-Gordon equation, applying the principle of stationary action, whereas varying with respect to the metric will define a stress energy tensor in a classical sense. So this long expression here represents the classical stress energy tensor for some scalar field with some mass m and some coupling between the field and the background curvature given by this constant x(z) here. And then what you want to do is you want to quantize your scalar field, and I won't do it in the sense of the last talk. I'm not trying to define this algebra of observables, but let me just do it in a kind of canonical sense, where we promote the field to an operator value distribution, which I'll represent just by putting a hat on the field, and then we apply something like equal time commutation relations. Okay, the second point here is not really relevant for what I want to say. The main point is that my field here has been promoted to an operator value distribution, and my stress energy tensor is quadratic in that field. So if I just replace my field here with its quantum equivalent, its quantum analog, which is an operator value distribution here, we have something that's that's quadratic in an operator value distribution and evaluated at the same space-time point. And of course, that's mathematically ill-defined. So we have to do something about that. So the right-hand side of our semi-classical equations, at least in a naive sense, is completely ill-defined. So they certainly can't represent the correct equations. So what we have to do is basically regularize this thing we're calling the quantum stress.
Bear in mind that we cannot see the cursor in the talk.
Okay? Oh, okay. Right, let me try to fix that. Can you see it now?
Now we can see it. Thank you.
Okay.
Thank you.
Yeah, thanks, Julio. Okay, so we need to regularize this thing, this quantum stress energy tensor. Okay, so the way to do this, or one way to do this, I should say, is called point-splitting regularization. So the idea there is, instead of considering a quantum stress energy tensor, which is some operator value distribution, we consider the limit or the coincidence limit of an operator valued by distribution. So it's going to be an operator value distribution at two space-time points, x and x primed. Now, eventually we have to take the coincidence limit of this thing, the limit of x as x prime goes to x, but let me ignore that for the time being. And we can express this by distribution as some differential operator, which I'm just going to label as theta hat, subscript AB, on some product of field operators evaluated at different space-time points, x and x primed. So provided x is not equal to x primed, this will be a well-defined quantity. It's only in the limit as x prime goes to x that this thing is ill-defined. And I'm defining my operator here in such a way that I get back the classical stress energy tensor expression in the classical limit at coincidence as x prime goes to x. Okay, so if we think about the quantity that's on the right-hand side of the naive semi-classical equations, semi-classical Einstein equations, which was this thing here, the stress energy tensor of some quantum fields in some quantum state A. And we pull the limit and this differential operator outside of the expectation value, then we can represent this quantity here, which is the source term in the semi-classical equations, as the coincidence limit of some differential operator acting on a two-point function or acting on a correlator, as referenced often in the previous talks. Okay, so like I said, provided we don't actually take this limit, this thing is well defined. All right, so in other words, if I just consider this object here without taking the coincidence limit, then we've regularized the stress energy tensor by defining this by distribution. Of course, we do have to take the limit at the end of the day. So then the question becomes, can we actually make physical sense of this particular limit, this coincidence limit? And by can we make physical sense, what I really mean is, can we remove the divergent terms here in a controlled way or in a renormalizable way, if you like? Can we reabsorb those infinities into some other quantities in the theory? And of course, that process of renormalizing these infinities or reabsorbing them into some other quantities in the theory is what we call renormalization. Now, that's not a particularly quantum idea. Of course, that idea of removing infinities and reabsorbing them into some redefinitions of the theory's parameters is completely ubiquitous in both classical and quantum field theories. So just to give a quick classical example, if one is trying to look at the force on an accelerating electric charge, for example, the force on the charge itself due to its own field, or in other words, the self force, then you quickly realize that the vector potential diverges at the location of the charge. And so you have to remove that infinity in some controlled way. And it turns out what you do is you subtract that infinity by reabsorbing it into a redefinition of the mass. So both the vector potential and the mass get renormalized, if you like, in that process, as was worked out by DeWitt and Bream many decades ago. So in the semi-classical picture then, which is the one we're interested in, we can't just throw away the infinity on the right-hand side here in an arbitrary way. What we have to do is we have to subtract out this infinity or renormalize this, but at the cost of renormalizing some other terms in the theory. And it turns out in order to actually do that in a consistent way, we have to introduce these higher curvature terms, or these terms that are quadratic in the curvature. And we really need these terms in order for the theory to be consistent. So what actually happens is we renormalize the stress energy tensor at the cost of renormalizing the gravitational constant, which I've kind of set to 1 here, I've fudged it a little bit, the cosmological constant, and these two coefficients of these quadratic curvature terms. So it's not the case that we take the naive semi-classical equations and we just replace the right-hand side with its renormalized equivalent. That's incorrect, even though many people write that down, even in papers, that's often written down that way. We really do need these other terms, these terms that are quadratic in the curvature. I haven't written them down explicitly. These are just two locally constructed terms that are quadratic in the curvature. Okay, so this is the only way that this idea really makes sense. So then the question I want to address is, how do we actually renormalize the stress energy tensor? How do we actually compute this in practice? So to do that, to renormalize the stress energy tensor, I'm going to use what's called a Hadamard renormalization prescription, which the previous talk referenced. So the idea is you restrict to a class of quantum states for which the Green's function has the so-called Hadamard property, which is this idea that for x sufficiently close to x primed, the Green's function has this universal form. Okay, so I'm labeling the Green's function by this subscript a here, which is a reference to the fact that it depends on the quantum state I'm interested in. And let me just quickly explain some of these quantities. So the 2 sigma here is the square of the geodesic distance, which in some coordinate expansion is just given by the coordinate length squared to leading order. This delta here is called the Van Vleck-Moret determinant. Again, it's just locally constructed. Intuitively, you can think about it as a measure of whether a geodesic congruence is converging or diverging. And the V here, again, it's a locally constructed symmetric biscalar. It can be written down in an expansion in terms of this world function here. Intuitively, you can think about it as just encoding information about how waves scatter off the curvature. So these 2 terms here are just depend locally on the geometries. Unlike the last term here, the W, which carries this subscript a to indicate that this does not only depend locally on the geometry. So this cannot be locally constructed. It actually depends on, for example, the quantum state. So it can't be obtained by some kind of local expansion. But importantly, it is symmetric in x and x primed. And it is regular at coincidence. So when the limit as x goes to x prime, this term here is regular. So let me also just mention, so this arbitrary length scale here that I put in the log term to make it dimensionless. So you can think about this as encoding the ambiguities that were mentioned in the previous talk. So changing this length scale, for example, corresponds to changing this term by some kind of local terms. We'll pick up some factor of v here. So this is the so-called renormalization ambiguity that's encoded in this length scale L. And then this plus I epsilon here is just necessary in order to define these terms as well-defined distributions or generalized functions. Because even when x is not equal to x primed, sigma here can be 0 when x and x primed is connected by a null geodesic. So this I epsilon here is necessary in order to render this a well-defined distribution. This first term here is sometimes called the direct part of the Green's function, and this is sometimes called the tail part of the Green's function. So if you hear me referencing that terminology later on, that's what I mean. Okay, so like I said, the first 2 terms here contain all of the divergences as x approaches x primed in this expression. So if we take these first 2 terms here and label them as another biscalar or bidistribution kx of x primed, we'll call that a Hadamard parametrics, or more accurately, a 1-parameter family of Hadamard parametrices parameterized by this arbitrary length scale here, L. So all the divergences in this correlator and this 2-point function are contained in these first 2 terms, which we'll call a Hadamard parametrics. So clearly then, if we want to render this object here finite, we want to get something that's finite in the coincidence limit, we can simply subtract the Hadamard parametrics from our 2-point function, which of course is going to be equal to W. I subtract the blue box here from the left-hand side. I'm just going to get left with this WA, which is regular in the coincidence limit. And then of course, if I subtract it, I have to add it back on again. And then I need to make sure that that this term here can be reabsorbed into some other terms in the theory in order for everything to be consistent. So fortunately, that turns out to be the case because everything here is locally constructed. That means everything here is renormalizable. So if I hit this Hadamard parametrics with my differential operator that appeared in the definition of my stress energy tensor by distribution, then I just get terms that involve the Einstein tensor, the metric, and these other terms that are quadratic into curvature. So what that means is before I actually take the coincidence limit, I can reabsorb all of the infinities in this into a redefinition of these other terms on the left-hand side of the semi-classical equations. So that really essentially solves the conceptual problem that point-splitting regularization and the Hadamard renormalization combined essentially solve the conceptual problem of how to appropriately define the semi-classical equations. So for example, just to complete that idea, so we replace the right-hand side now in the semi-classical equations with the renormalized stress energy tensor in some quantum state A, which is the square brackets here just mean the coincidence limit, just a shorthand for the coincidence limit. It's just now this differential operator acting on the WA here. And of course, you actually compute the WA by just subtracting the Hadamard parametrics from your 2-point function. So that essentially solves the conceptual problem, but there actually remains kind of a stubborn practical or computational problem. And to see what that problem is in practice, we note that, for example, let's say we're just in some static spherically symmetric spacetime, then this 2-point function here, this green function here, will be represented as some mode sum expression, which is kind of globally valid. The PL here are just the Legendre polynomials, and the G omega L here is just some one-dimensional radial Green's function. And to compute this, of course, you typically, at least in any black hole spacetime, you actually compute this numerically. So the radial modes typically aren't known in terms of known functions, so usually you compute this numerically. And the divergence here in the coincidence limit as x prime approaches x manifests itself in the fact that if I take or going to or prime, if I take delta tau going to 0 and I take gamma going to 0, then this sum and this integral won't converge. So in other words, the divergence, the short distance divergence in this expression is manifest in the fact that this mode sum doesn't converge. On the other hand, I want to subtract this Hadamard parametrics from this expression. But this is just an expansion in sigma. It's a local expansion. And the divergences as x approaches x prime in this expression are just kind of manifest in the explicit geometrical expansion, if you like. So the computational problem is kind of simple to state. It's how do I actually subtract this locally constructed parametrics from this mode sum expression in such a way that the coincidence limit can be meaningfully taken. And that turns out actually to be quite a stubborn problem, and it seems like a simple problem to state, but it's been quite a tricky problem to solve, as Noah Zilberman mentioned in our talk earlier this morning. It's kind of been a long-standing problem. Now, the first resolution, at least practical resolution that I know of, came from Candelas and Howard, who looked at a massless scalar field in Schwarzschild spacetime. And they developed this kind of method, which was later extended by Anderson, Hiscock, and Samuel in the 90s. And to give you a basic sense of the idea, what you do, first of all, is you work in a particular quantum state called a Hartle-Hawking state, which is a thermal state. And because it's a thermal state, it satisfies the KMS condition. So you can actually work in the Euclideanized version of the metric, which for some technical reasons that I won't go into is actually easier. So you work with the Euclideanized Schwarzschild metric, and then you notice that you can point split in any direction that you like. And it seems, at least naively, that things are much easier if you take the partial coincidence limit, where you take the spatial points together and you only point split in the temporal direction. At least naively, that seems like a simplification. And so what you get then, if I write down the Green's function for the massless scalar field on the Euclidean Schwarzschild metric, you can represent the Green's function in a form like this, after a little bit of massaging of the expression. The P and Q here are just homogeneous solutions to the radial wave equation, where P is regular at the horizon and Q is regular at infinity, and N is just some normalization constant. And delta tau here is just the separation in the Euclidean time direction. Kappa here is the surface gravity of the black hole. So that's the Green's function, the globally valid Green's function, written as a mode sum. And of course, you get discrete modes here because you're working on this Euclideanized slice, which is one of the reasons it's easier to work on this slice. On the other hand, the Hadamard parametrics separated only in the time direction. The only singularities you get come from the direct part, because the tail part is order delta tau to the 4 for a massless scalar field and source field. So the only singularities you get are very simple. It's just this term here. So this is the only term that you need to subtract from this Green's function in order to regularize this thing. Okay, so that all seems quite straightforward, but the problem again is, how do I actually subtract this 1 over delta tau squared from this mode sum expression in such a way that the coincidence limit can actually meaningfully be taken? And the Candelas and Howard idea is to take a Fourier transform of this 1 over delta tau squared. In other words, express it in some set of modes that are similar to these modes, and then try to subtract mode by mode. Okay, again, that seems straightforward enough to do. So if I subtract this from this and I take the coincidence limit, that's a quantity known as the vacuum polarization, or the expectation value of phi squared. This is all in the Hartle-Hawking state again, as I already mentioned. So if you like, you can think about this as the coincidence limit of that quantity W that I mentioned earlier. So this is the expression you'd get as a mode sum if you actually do that. But again, that kind of solves the problem, but not quite, because what you've done there is you've managed to bring this 1 over delta tau squared inside the N sum, but not inside the L sum. So this is not a complete mode by mode subtraction. And this in fact isn't really, even though this is formally regular, this is not amenable to a numerical computation. There's real subtle cancellation that's required here between this infinite sum here and this other term here. And this is a very slowly convergent L sum, by the way. So you really need, even if you computed tens of thousands of modes, which would be computationally really expensive because these have to be computed numerically, you're still not going to see the cancellation between this term and this term. So as it stands, this isn't even amenable to a numerical computation. So what Candelas and Howard did then, and this is kind of the ingenious part of their step, is that they treat the L sum quasi-analytically. So they take this L sum and they subtract some high order WKB expansion, which is some large L expansion for this particular radial Green's function here. So you subtract the WKB and you add it back on again. Okay, well, this term here now is going to be rapidly convergent by definition of the fact that this is a large L expansion, a large L approximation to this Green's function. And this term here, you can basically treat quasi-analytically. What you basically do is you convert the L sum into an integral in the complex plane using the Watson-Sommerfeld transform. And then, without going through the nitty-gritty details, essentially what happens is parts of this integral here in the complex plane can be done explicitly, and all of the singular terms or the apparently singular terms cancel, and indeed even the slowly converging terms cancel, and you end up with something that actually is computable in practice. So it's quite an ingenious solution, and it was the first kind of practical solution of its type, and in fact remained pretty much the only pragmatic solution to computing quantum expectation values in black hole spacetimes for about 30 years or so. Despite the fact that even though it is quite ingenious, it has some real obvious drawbacks. So it's quite inefficient and cumbersome to implement. The convergence, as we saw on the previous slide, is not even explicit, because you don't have this complete mode by mode subtraction. You actually have to do quite a lot of work, and you really have to use the Watson-Sommerfeld transform and convert these things to integrals in the complex plane to actually see that the object actually is convergent. And one of its more serious drawbacks is that it relies crucially on the WKB approximation, which is not uniform. And by that, I mean that as you get closer to the horizon, which is often the place where you're really interested in anyway, as you get closer to the horizon, you need more and more modes in order to see the convergence. So the convergence properties get worse as we approach the black hole horizon. So that's kind of also a problem. So the question is there a more direct approach? So there is, and actually there's been a couple of new approaches that have kind of come on stream in the last, I'd say only the last 6 or 7 years. One is by Amos Orzi's group in Technion in Israel. So they've done some really great work on what they call the pragmatic mode sum prescription. And then another quite different prescription is the one that I'm going to describe today. So this is an idea that myself, Cormac Breen at TUD, and Adrian Ottawell at UCD have been working on for a few years. So the idea is so let me just focus on the vacuum polarization, not the stress energy tensor for now, because all of the real key details are in there already. So really what I want to do is obtain a complete mode by mode subtraction. In other words, I want to be able to express the Hadamard parametrics as an n and l sum, so that I can subtract mode by mode. And what I want at the end of the day is something that's very, very that converges very fast. So that's really what I mean by a pragmatic solution to this. So here's 2 key considerations in obtaining a complete mode by mode subtraction. The first is actually it's just better off, it turns out, to point split in multiple directions. So even though it seems simpler initially to point split only in one direction, in the time direction, because you can write down your Hadamard parametrics very simply in that case, that initial simplification turns out to hurt you when you want to express that as a mode sum. And then the second thing is don't expand in coordinates, in ordinary coordinates, or at least in the usual polar coordinates in which we write down the source geometric. But it turns out to be better to expand in what we call extended coordinates, which are these expansion parameters that are adapted to the geometry of the spacetime. So rather than expanding in, so what we do is we point split only in there, or we point split in all directions except for the radial direction. So we take the partial coincidence limit where we take the radial points together. So that's some simplification, but we keep all of the other directions apart. And then we expand in these parameters w squared and s squared. To leading order, w squared is just the separation in Euclidean time delta tau, and to leading order, the s squared here is just 2 sigma. All right, in other words, just the square of the geodesic distance when or is equal to or primed. So it turns out to be very useful actually to expand in these parameters. I mean, you need a little bit of foresight to understand why these are the right things to expand in. But if we expand in these parameters, we can write down the Hadamard parametrics to some order in the following form. Okay, this seems complicated, but let me explain some of the terms here to you. So I'm expanding the Hadamard parametrics in these parameters w squared and s squared. So the top line here are the terms in the Hadamard that come from the direct part of the Hadamard parametrics, the delta to the half over sigma, if you like. And there's only really 2 types of terms that show up. There are terms that are rational in w squared and s squared. So hence I labeled these coefficients here with a superscript or for rational. And there are terms that are polynomial in w squared and s squared. Similarly, they're in the tail part of the Hadamard parametrics, the v log sigma term. There's only 3 types of terms that show up. There are terms that are rational in w squared and s squared. There's a log term that shows up because you have a log sigma. And there are terms which are polynomial in w squared and s squared. And I've expanded here to some order epsilon 2m log epsilon, where epsilon is just the coordinate distance, if you like. Yeah, so this upper limit here is just the expansion order that I'm taking. Okay, so what I want to say here is that there's really only 2 types of term here in this expansion that I need to convert into a mode sum. I don't need to convert anything that is polynomial in w squared and s squared. So for example, if I want to do a multipole decomposition of terms like this, in that sense, I would be doing a decomposition in these Legendre polynomials, PL of cos gamma. But of course, if these are polynomial in cos gamma, then there's not going to be a large L contribution, right? I could represent these as a finite sum in terms of these Legendre polynomials. So these polynomial terms aren't going to have a large L or a large N contribution if I express them as a mode sum. So I don't need to convert these into a mode sum. They're not going to contribute to the large L or large N behavior of the mode sum, which is exactly the behavior we're trying to renormalize or regularize. And then the other type of term, of course, the other type of singular term is just these log terms here. So I only need to really convert these rational terms and this log term into a mode sum. So the only question then is, can we express these as mode sums? So what I mean there is, can I represent these in the same set of basis modes that the Green's function were in? And if I can, then I can do a subtraction mode by mode. And it turns out, now the devil is kind of in the detail here, so it turns out that I can express these terms and these terms in exactly the same set of basis modes that my Green's function are in, and I can derive all of the so-called regularization parameters in terms of known functions, in fact. So in other words, if I express these kind of rational types of terms in this kind of multipole decomposition and Fourier transform, can I actually invert this to determine these kinds of regularization parameters in closed form? Can I invert expressions like this? And it turns out that you can do that. And it's kind of a complicated exercise in special functions, of course, and I certainly won't be going through the details, but if you're interested in the details, you can read the paper where these details are worked out. So it turns out both these psi regularization parameters and these chi regularization parameters can be determined in closed form or in terms of known functions. So for example, I can invert the top expression here to obtain this expression for the psi terms. Okay, so I just get some derivatives of some finite sum of a product of associated Legendre functions, where this eta term here is given in terms of the metric function f and the surface gravity kappa. Like I said, it's kind of a long derivation. There's no point in going through it here, but it suffices to say here that these regularization parameters can be determined completely in terms of known functions. And similarly, though I'm not going to write them down because they're a bit longer to write down, these chi regularization parameters can also be written down in terms of products of associated Legendre functions, though the expressions are a little longer and cumbersome to write down. Okay, so that's really the resolution, if you like, of the problem, because essentially now we can express the Hadamard parametrics in terms of this mode sum, where these K and L subtraction modes here is just some combination of these psi and these chi regularization parameters that I wrote down on the previous slide, and then plus we have some closed form terms which are polynomial in W squared and S squared, which I don't need to convert into a mode sum. So I only need to subtract this term from the mode sum, if you like. So that gives me, for example, a complete expression for the renormalized vacuum polarization. I subtract this mode sum representation for the Hadamard parametrics from the globally valid mode sum representation of the 2-point function, and I take the coincidence limit. And so what I get here is this mode sum expression plus some term which comes from the coincidence limit of these polynomial terms. Okay, so this, if you like here, this is much better than, much more convenient than the Candelas and Howard approach, because what I have here is a complete mode by mode subtraction. So I don't need to do anything fancy here. I just need to evaluate this thing directly. And what's more is, the higher I take this n term here, the higher I take this order in the Hadamard parametrics, the expansion order in the Hadamard parametrics, the faster this thing converges. So I have complete control over how quickly this mode sum here converges. So for example, for a fixed L and large n, this difference here is going to converge like n to the minus 2m minus 3. Whereas for fixed n and large L, it's going to converge like L to the minus 2m minus 3. So if you take a sufficiently high order in m here, this thing will converge extremely rapidly. More importantly, and even more impressively in a certain sense, is that the convergence appears to be uniform. It does not depend strongly on whereabouts in space-time we are. In particular, this convergence is not affected by approaching the horizon. So even when we evaluate a point close to the horizon, we still get this very, very, very rapid convergence. Let's just show you some quick plots here. So this is for these plots are for a massless scalar field and source field. So if I take fixed L and just plot the large n behavior of the Green's function here minus the 0th order subtraction term as a mode sum, and I multiply by n cubed here, and I take the log of it, the log of the absolute value of it, I get a straight line as n is getting large, which is telling you that this difference here in the curly brackets goes like 1 over n cubed for large n and fixed L. Similarly over here, if I subtract at order 1 here, so we take all of the terms in the Hadamard parametrics up to order 1 and I subtract, I get something that goes like 1 over n to the 5. And this plot here is showing you what you get when you subtract everything up to order 2 in the Hadamard parametrics. And it does exactly what you'd expect it to do. It converges like 1 over n to the 7. So very, very rapid convergence that we have complete control over. Okay, and this is just a plot of the vacuum polarization for a massless field in Schwarzschild, and the dotted lines here are just tabulated data from the Candelas Howard paper in the 80s. And this is just, I just give this to show you that our results, which are the solid line, agree exactly with the Candelas Howard method. Okay, that's the essence of the method. Again, what turns out to be quite remarkable is that usually in these contexts, you have to work really, really hard to upgrade this computation of the vacuum polarization to the calculation of the renormalized stress energy tensor. Even though all of the essential conceptual details are there, just the added computational complexity in moving the stress energy tensor is usually quite high. But in fact, you can actually do it with fairly little additional computational complexity. So if we write down the renormalized stress energy tensor in terms of coincidence limits of this Hadamard W that I wrote down earlier. This term, and this term just involve derivatives of the coincidence limit of W, and the coincidence limit of W is just a vacuum polarization. So I've already shown you how to compute that, and we can compute that really, really rapidly. Whereas the first term here is a tensor WAB, which involves the coincidence limit of two derivatives of W at the same spacetime point, either at the x point or at the x prime point. So this is the only term that we actually need to compute. All the other terms we can compute just from derivatives of our expression of the vacuum polarization, which we've already shown how to compute very, very efficiently. I should also point out here that the last term here it wasn't in the first expression for the stress energy tensor that I wrote down at the beginning. So this term has to be added on in order for the stress energy tensor to be conserved. And the V1 here is just some geometrical term, some locally constructed term. So I need to add this on in order for the stress energy tensor to be conserved. And I need the stress energy tensor to be conserved in order that the semi-classical equations are actually self-consistent. Okay, so we only need to really worry about computing this first tensor here, WAB. But it turns out that you can apply Singh's rule to simplify this term. So Singh's rule is just a rule for commuting derivatives and coincidence limits. So I can actually rewrite this term as two derivatives of the coincidence limit of W, which I know how to compute. Minus the coincidence limit of two derivatives of W, but at different space-time points. And that's much easier because these are just partial derivatives, because it's at two space-time points, and this is a scalar with respect to x and x prime. So that makes life a lot easier. Again, I don't need to worry about computing this because this is just derivatives of my vacuum polarization. So now all I really need to do is worry about computing this thing. When my two derivatives are at two different space-time points, this is actually straightforward to compute, at least when I'm taking derivatives along a symmetry direction of the space-time. So for example, if I just take two derivatives at my Euclidean time, tau prime and tau, the only effect that has on the previous computation that I showed you is that it just brings down two factors of n kappa. But remember, this sum here is really, really rapidly convergent. So this is still going to converge very, very rapidly, provided I pick an m that's large enough.
Peter,
plus
you
some.
have a few more minutes, okay?
How many more minutes, Ilya?
A few more. We are running out of time already.
Okay, sure. Yeah, so this term can be computed very easily, and then similarly, for if I compute derivatives in the phi direction, all that actually does is it brings down a factor of L plus 1, so that's also very rapidly convergent. And I have some terms that are polynomial in my W squared and S squared, which I can compute very easily. So the only thing that remains to compute then for the stress energy tensor is the W or term, and I can actually just compute that directly from the wave equation once I know these terms. So again, that presents no problem. So all I'm really saying here is essentially, with very little additional computational complexity, I can compute the renormalized stress energy tensor essentially from my computation of the vacuum polarization with just these two added terms to compute, which are really straightforward to compute. So let me quickly show you some results in Schwarzschild, applying these results to Schwarzschild. So here I'm showing some 3D plots of some components of the stress energy tensor as a function of OR and a function of the coupling. So one of the reasons I'm showing you these plots is that our method is really so efficient and so accurate that we can really do these three-dimensional plots in a matter of a few hours on a standard laptop computer, which you know, in the 80s or 90s was kind of unimaginable. But our method now is really so fast that we can really do this very straightforwardly. And it's really a matter of routine. So these are some 3D plots, and this is just giving you, I guess, some values for some different couplings of one of the components of the stress energy tensor. And again, this is a plot of one of the components of the stress energy tensor in Schwarzschild as a function of the radius and also as a function of the mass. And again, I'm really just showing you this just to show you in a certain way, in a certain sense, just to show off just how efficient the method is that we can do these 3D plots really in a matter of hours on a standard laptop computer. So some other things you can kind of compute from our methods, you can look at things like energy conditions, quantum energy conditions in Schwarzschild. So for example, here we're looking at the null energy condition for an observer on the photon sphere in Schwarzschild. So UA here is just a 4 velocity on the photon sphere in Schwarzschild. So we're just projecting the components of the stress energy tensor onto this particular orbit. And we're computing that for a bunch of different masses. Yeah, we find here that basically everything here is positive unless you take xz to be enormously large and negative, in which case the semi-classical assumption will be violated anyway. So I'm just pointing out the fact that we find no evidence of null energy condition violation here, which is contrary to some results that Amos Ori and Adam Levy found for the Unruh state in Schwarzschild. So interestingly, we don't find any evidence of the null energy condition violation in our case. And then lastly, just to wrap up, we can also actually do back reaction calculation. Again, just because our method is extraordinarily fast and extraordinarily accurate, we can compute the stress energy tensor to like 12 decimal places of accuracy in a matter of hours. Which means we can actually use those numerical expressions to numerically integrate the semi-classical equations and actually obtain the back reaction. So here I'm just plotting. So this is the perturbation of the metric to first order in H bar, and these this function rho and zeta here basically contains some combination of the expectation value of the stress energy tensor. So the numerically evaluated stress energy tensor is contained in these two functions here. And the solid line here represents our numerical solution and to the back reaction equations, and the dashed line here is just Page's approximation. So this is for a massless conformally coupled field. And we can actually see that the Page approximation actually does pretty well here actually, compared to the exact solution. And then maybe I'll leave this maybe because I'm running out of time. So again, this is just some plots of back reaction for different field masses. And I'm running out of time, so let me just quickly leave you with some conclusions. So the broad perspective here is just that after decades of stagnation, we actually have a suite of new methods now to accurately and efficiently compute the OR set. Both the method that I've presented here, but also the methods that the group in Technion have also come up with. And then some takeaways on our particular method. It turns out that splitting in multiple directions is actually really useful. And then if you expand in a judicious choice of expansion coordinates, then you can compute all of these regularization parameters in closed form. The resultant mode sums are rapidly convergent and actually also uniformly convergent. And then let me also just mention some ongoing work to extend this to other quantum states, to stars with Julio Arrechea, higher dimensions, with Cormac Breen and his PhD student, cosmological spacetimes, and working with Antonio Ferrero to extend these ideas there, and also to CARE with Adrian Ottawell and Cormac Breen. Okay, sorry for going over, and thank you for your attention.